Hey everybody, welcome to 12.1, the Fundamental Counting Principle and Permutations. So chapter 12 is going to be all about different types of probability, and today we're going to talk about how to count possibilities for numbers of items, and I'll explain more in just a little bit, but here's in general an example of what we're doing. A deli offers 4 types of meat: ham, turkey, roast beef, pastrami, and 3 types of bread: white, wheat, and rye. How many sandwiches are possible if you choose 1 bread and 1 meat? So what we're going to do is figure out how many different sandwiches could I make. And I'm going to show you what this would look like if I was going to try to do this by hand. You do not have to write this down because I'm going to show you the shortcut in just a little bit. Just want to show you, if I didn't know this shortcut I'm teaching you today, I would have to figure this out by hand. So maybe I would start by writing down, okay, I could have ham, turkey, roast beef, pastrami. Again, you don't have to write this down because this is the longhand way, and we're not gonna use this. You could use it if you forgot the shortcut. But normally I wouldn't recommend it. For each one of the types of meat, I have 3 choices of bread. So I could have ham on white, I could have ham on wheat, I could have ham on rye, and I can do that for each one of my bread types, or meat types, I mean. I could have roast beef on white, I could have roast beef on wheat, I could have roast beef on rye, and basically, once I make this thing, it's called a tree diagram, I would count up how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, how many things I counted for my last category, and there's 12, so the answer is 12. There is a much faster way of doing it, and it's called using the fundamental counting principle. So this we use if I have different events or different categories that I'm selecting things from. Later we're going to talk about what to do if I have one category that I'm selecting a group from. But here's where we're picking one thing from each of different categories. So here's what we're going to do. We're going to take the number of ways or the number of types in category 1. And let's say that in this case category 1 would be type of meat. So it would be 4. We're going to multiply that by the number of items in category 2. And if I had lots of different categories, I'd just keep going. I would just keep going. The number of things in this group times the number of things in this group times another thing in this group, and so on. Our example then is, my first category is the meat category, and I've got 4 items. My second category is the bread category, and I've got 3 items. And I'm done there because I only have 2 categories. 4 times 3 is 12. That's my answer. Once you know how to do fundamental counting principle, it can make these problems really fast. It does get slightly more difficult. Let's go to example 2. So now I have a standard Minnesota license plate. It's 3 digits followed by 3 letters. My question is, how many different license plates are possible if digits and letters can be repeated? And just so you know, in case you forgot, there are 26 letters in the alphabet from A to Z. And we consider it 10 digits because you may have been thinking 9 because 1, 2, 3, 4, 5, 6, 7, 8, 9. We include 0. So if you include 0, there's 10 digits. In this situation, some of the categories are repeated, but that's okay. It said I'm going to do 6 things because I'm going to do 3 digits times 3 letters. So that means I need 6 blanks total. And so the first 3 blanks are for how many digits I could possibly select. And then my last 3 blanks are how many letters I could possibly select. Alright, and I just told you there's 10 digits. So there's 10 digits in that group, and we're saying that it can be repeated. So it's the same group again. I'm just going to pick again from the same group. So still 10, still 10. And then there's 26 things in the letter group. So 26, 26, 26. And again, I can have repeats, so I have the same number each time for the letters. Now all I do is type that in my calculator. You end up with 17,576,000 license plates, which really isn't that many if you think about the fact that the population of Minnesota is what, 6, 7, 8 million nowadays, and a lot of families, or we have at least one car per person in the state, so we don't actually have that many more possibilities than we have cars in Minnesota. It's kind of interesting. All right, anyways, how many different license plates are possible if digits and letters cannot be repeated? So same situation, I still got 6 blanks because I'm going to have 3 digits and 3 letters, but here's the deal. It cannot be repeated. So the first time I pull from the digits group, I've got 10 digits still. But now, because I've already used 1, I now only have 9 digits left from that digits group. I used 1 of them already. And once I've pulled out that, I now only have 8 left for the second or the third draw. Something similar happens with my letters. So I start out with 26 in the group, 26 letters in the group. I took 1 out, it can't be repeated, so now there's only 25 left for me to pick from. Once I pulled 2 out, there's only 24 left for me to pick from. And when I multiply that in my calculator, I get 11,232,000. All right, make sure as we're going along here, on the side, write down some questions you might have, and then you can ask me in class tomorrow and we can talk about it. All right, let's do example 3. Police use photos of various facial features to help witnesses identify suspects. Wow, struggling with my reading this morning. Okay, one basic ID kit contains 195 hairlines, 99 eyes and eyebrows, 89 noses, 105 mouths, and 74 chins or cheeks. The developer says he can produce billions of faces using this kit. Our question is that true? All right, so we want to figure out how many different faces could someone create with these different elements. So if you think about it, I've got the hairline group that I could pick from. I've got the eye group. I've got the nose group, and eyes and eyebrows are in the same group. I've got the mouth group, and then I've got the chin or cheek group. So there's 5 different categories of information they gave us. So it said 195 hairlines, 99 eyes, 89 noses, 105 mouths, 74 chins or cheeks. And I got that just from the information they just gave us. And again, fundamental counting principle, multiply together the number of items in each category. So this is how many items are in the hairline category, how many items are in the eye category, and so on. Anyways, when you multiply that together, you actually do end up with billions because it's 13,349,986,650. So there are billions. Pretty amazing how many different faces there are in the world, though. Everybody's different. Okay, now let's make it a little bit different. Part B, a witness can clearly remember the hairline and eyes and eyebrows. How many different faces can be provided with this info? Okay, so here's what you got to think of. What they're telling us is that for the hairline category and for the eye category, our suspect knows which one to pick. So it's not the fact that, oh, there's 195 it could possibly be. No, he knows or she knows specifically which one it is. So there's only one possibility because they're certain on that. And same thing with eyes. They're certain on which set of eyes it is. So those ones are for sure. So it's just one. And really, you wouldn't even need to write those down. But I am, so you can kind of see what's going on here. Then the suspect doesn't know this other stuff, or the witness, I mean. So there's 89 noses, 105 mouths, 74 like before. Those are the categories they don't know, so we still have to pick from all of those. Multiply those together, and there's 691,530 faces. So it actually cuts it down quite a bit, but there's still thousands and thousands and thousands of faces for the witness to try to identify. Once again, write down any questions you have. Now we're going to move on to something called factorials and permutations. So first of all, sometimes when you're doing this fundamental counting principle, you might get into a situation where I have something like, for example, 10 times 9 times 8 times 7 times 6 all the way down to 1. And instead of typing that all into our calculator, there's a shortcut button, and it's something called a factorial. So right now, this is just a math fact I'm about to teach you. Just a math fact, a math operation you need to know how to use. So what a factorial is you multiply a number by itself and every number below it down to 1. So for example, and by the way, the factorial symbol is an exclamation mark. So this doesn't mean 6. It means 6 factorial. That was one of my best math jokes, in case you're wondering. Okay, so 6 factorial, that's how you read it. And it's kind of like, for example, we have a symbol for square root. You know what I mean? We have a symbol for squaring something. I mean, this is just another math number operation. So this operation of factorial means that I need to do 6 times 5 times 4 times 3 times 2 times 1. And I want to tell you that on your calculators, on your calculator, and I don't know if this program I'm using can handle this calculator, so we'll see what happens here. To find the factorial button, you're going to hit Math, so the Math key right under Alpha. You're going to scroll over until you're at PRB. It stands for probability. So again, this is our probability chapter. All this stuff is under the probability section, and you select number 4. Now I have a problem here, and that is I have not yet typed in my numbers. So before you select that, you're going to want to type in the 6 so that you do 6 and then the factorial. So see, that's not going to work for me. Okay, so I'm going to go back to 6, then the factorial, and the answer is 720. Now alternatively, I could have just typed this all in, and it's really not that bad for this one. Once you get up to ones that are 12 factorial or 13 factorial or something like that, it is very laborious to have to type them all in. So you can use the factorial button. Just another example in case you're not really sure what we're doing yet. Only write this down if you need to. For example, 4 factorial would be 4 times 3 times 2 times 1. So you just take the number itself and everything below it. In official math language, here's what the formula looks like. It is n factorial equals n, so that's our number, and then the number that's 1 below n, the number that's 2 below, and so on. So if you see that in the book, that's the mathematical way of saying what I just taught you. And then here's one definition that you need to know and memorize. 0 factorial is defined as 1. 0 factorial is defined as 1. Very similar to how we have some of these other rules, right? Anything to the 0 power is equal to 1. For a different reason, but a similar property, so maybe that might help you memorize it. I'm going to stop there and talk about permutations in the second part of the 12.1 video. Thanks for watching. Hey, welcome back everybody. This is 12.1 Part 2, also known as 12.1 B. Alright, so now the reason I showed you factorials at this time is we use factorials when calculating something called a permutation. What I just talked about with fundamental counting principle was when I had different categories of things and I wanted to pull one thing out of each category. What we're going to talk about with a permutation is what I want to do when I pull multiple things out of a single group. I'm going to say more about that as we go along. In a permutation specifically, when I pull these things out of a group, we want to order the objects in a specific way. So a general definition of permutation is a ordering of objects. The key word that you want to think about when you think permutations is that order matters. Order matters is the key word you want to think about. So here's what I mean by ordering objects. Let's suppose that I had the letters A, B, C. So what I'm going to do is I'm going to find all of the permutations of the letters A, B, and C. So I'm finding the permutations of the letters A, B, and C. Alright, A, B, and C. Here's all the ways I can rearrange them. That's basically what I'm asking for, all the ways I can rearrange those letters. So I can rearrange them ABC, I could do ACB, I could do BAC, I could do BCA, I could do CAB, I could do CBA, and that's it. So if I was going to ask you how many permutations are there of the letters ABC, there are 6. There are 6 ways I could rearrange those letters. So there are 6 permutations. So again, a permutation is us selecting some items and rearranging them. So specific order. There are 6 permutations of those letters. There is a formula for permutation, and here it is. I call this NPR. P is a normal letter, and N and R are both subscripts. N represents the number of items in the group you're selecting out of. So I'm going to say number in the large group. Number in the large group for N. And for R, it's how many I want to select and rearrange. How many we select and rearrange, and it's always specifically arranging things because we have another thing called a combination, which is only selecting only. So N, how many are in the large group, R, how many we are selecting and rearranging, and here is a formula. I do N factorial divided by N minus R factorial. Make sure you have that written down correctly. Now, I put that on that page because I was running out of space, but when we flip over to the back, I'm going to copy it down at the top as well, and I would recommend you do so that we have it when we're doing the rest of our notes on the back side here. All right, pause to write down or flip to the back when you're done. So again, I'm going to just write it over here so we've got it. NPR equals N factorial over N minus R factorial. All right, and this is just another shortcut that I can use to count items. And one thing that's somewhat confusing to students sometimes is that a lot of these problems actually have multiple ways that you can do them. Example 4 is the first type that's like that. It says 12 skiers are competing in the final round of the Olympic freestyle skiing aerial competition. How many different ways can the skiers finish? As in first, second, third, fourth, fifth place. Okay, so I could do this using the fundamental counting principle. And here's what I would think if I was doing fundamental counting principle, what we learned on the front page. There's going to be 12 skiers total, so I would have 12 blanks. And I'll write more in a little bit. I'm talking about how many ways can they finish. So this would be first place. How many people could I pick for first place? Well, there's 12 when I start out with. But once one person has gotten first place, there's only 11 people left to get second place, 10 people left to get third place, 9 people left to get fourth place, and so on. And so this is going to keep going all the way until I get to my very last person who is getting 12th place. Now, instead of typing all of that into your calculator, that is the same thing as doing 12 factorial because it is itself and every number below it. 12 factorial okay, that would be 479,001,600. And so that we just did that problem using the other stuff we learned. Now I'm going to do the problem using the new permutation stuff we learned. So if you wanted to use a permutation, here's what you would want to think of. I've got 12 people in my group, and this time I am taking all 12 of them and rearranging them in order of finish. So 12 in the group, all 12 are being rearranged. And if I typed that into my calculator, or if I used the formula, I would get the same answer. So let me show you something really quick. Let's use the formula. So N is 12, and R is 12. Here's what happens. 12 minus 12 is 0, And math fact that you need to have memorized, 0 factorial is 1. So that whole thing is just equal to 12 factorial, same thing we got when we did it with the fundamental counting principle. So again, there are several methods to do some of these problems, which makes it kind of confusing for some students, honestly. Let's do another one. Okay, part B. How many ways can 3 skiers finish first, second, and third place? So here's what you want to think of this time. I'm taking all 12 skiers in my group still, but this time I'm only selecting 3 of them. I'm only selecting 3 of them, and I want to see how many ways could they finish in these different places. So I am specifically arranging the people. So if I'm going to use my formula, again, 12 is n, and r is 3, and I'm using this formula up here when I'm plugging this in. And I'm going to show you how you can do this by hand, and then I will show you how you can type it into your calculator. 12 minus 3 is 9. So here's what's happening. If I was going to do this by hand, if I was in an emergency situation, didn't have my calculator, we know 12 factorial is 12 times 11 times 10 times 9 times 8, so on and so on. 9 factorial would be 9 times 8 times 7 times 6, and so on. You may notice I have a 9 on top and a 9 on bottom. I got an 8 on top and an 8 on bottom, but anything divided by itself is equal to 1. So essentially all of these things from 9 all the way on down are all going to cancel each other, and only 12 times 11 times 10 are left over. And if I'm going to do this problem by hand, that's really not that bad to type in my calculator. That's just 1,320. Alright, let me show you how to type this into your calculator now. So let's suppose I want to type 12 permutation 3 into my calculator. Here's what we're going to do. In your calculator, first type the number 12. First type the number 12. Then go back to that math probability section we were at before, and it's NPR. That makes sense, huh? And then type in a 3. And if your calculator is fancy, it might actually plug in the 12 for N and the 3 for R. Mine's not fancy, so there I am. 1320, voila! Same answer I got when I did it the by hand way. Cool. Let's do another example. Example 5. You have 5 different homework assignments to complete this weekend. The question is, how many ways can you complete them? So when they say something like this, they're talking about us taking 5 assignments. I am going to select all 5 and rearrange them. So I'm selecting all 5 and rearranging them. Alternatively, if you look at part B, and how many ways can you choose 2 assignments to complete on Saturday, out of the 5 assignments, now I'm only selecting 2. So hopefully you see the difference. Here I'm rearranging all of them. Here I'm only going to select 2 of them and rearrange them. I'm going to pause the video. Why don't you pause and type that into the calculator or do it by hand and see if you can get the correct answer right now. Alright, check your answer. See how you did. So we should get 120 for example 5A and 20 for example 5B. Again, please mark these if you want me to do these in class so that you will remember tomorrow which ones to ask me about. Example 6, I'd like you to read this one and see if you can get the setup and the answer on your own before I say anything. So pause right now and try these 2 problems. Alright, if you have unpaused, example 6A, you should have 10 permutation 6 for your setup, and the answer is 151,200. And for part B, you should have 10 permutation 10, which is 3,628,800. Again, write down questions if you have any. Last but not least today, we're going to talk about something called distinguishable permutations. So let me give you an example really quick to tell you why I would need something like distinguishable permutations. So for example, this one is optional to write down. You can just watch if you want to. Let's say that the library has 3 copies of the book New Moon. And they have 2 copies of The Hunger Games. On the shelf, you want to figure out how many ways you can arrange these. Let's assume that both copies of The Hunger Game looks exactly alike from the outside. Let's assume all 3 copies of The New Moon look exactly the same from the outside. So for New Moon I'm going to say N, and for Hunger Games I'm going to say H. So let's say that I'm going along, I have the books arranged like this. Then I'm going to go along and I'm going to arrange the books like this. And what happened was I took this copy of the Hunger Games and I moved it over there, and I took this copy of the Hunger Games and I moved it over there. But those two arrangements, if you hadn't known I had moved the two books, it looks exactly the same. Doesn't look like anything changed. So the thing is, if I want to count how many distinguishable, that means how many things are actually different from each other, I don't want these repeats that happen if two of the items that I'm rearranging are exactly the same. So distinguishable, I don't want those repeated things. So my formula for distinguishable permutations is a little bit different here. We're still going to have on top n factorial, the number of letters or things being arranged. So that's still the same as before, or the number of items in the large group, I could also say. But here's what's going to happen. On bottom, we're going to divide off. We're going to divide off the things that repeated themselves. So I'm going to call this Q1 factorial, Q2 factorial, and so on. And this is a little confusing, so please make sure that you ask me tomorrow to talk about this more if needed. I'm going to kind of run out of time here, so I might need to anyways. And Q is the number of times that that thing is repeated. So let me show you an example to make it more clear. Example 7a, find the number of permutations of the letters in the word Connecticut. Okay, so first of all, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 letters, so n is 11. And then here's what I mean by this Q1, Q2, Q3 stuff. If I look at this word, there are 1, 2, 3 C's being repeated. So to divide off all of the extra rearrangements that are not distinguished from each other, I use a 3. So 3 represents the fact that there are 3 C's. And then I look and what other letters are repeated. Let's see here. It looks like the N's are. There are 2 N's. So I'm going to have 2 factorial to represent the N's. Then there's also 2 T's. So I'm going to have 2 factorial to represent the T's. And then one way you could think about this is there's only one O, there's only one E, there's only one I, and so on. So really it's 1 factorial, 1 factorial, 1 factorial for all those letters that don't have repeats, but when I multiply by 1 it doesn't change it at all. This is my setup that I type into my calculator then, and last cautionary note I want to give you, when you're typing in factorial, you need to put these in parentheses. If I don't put these in parentheses, I will get the wrong answer. Please right now try typing that in and seeing if you can get the correct answer. You should get 1,663,200. And number one mistake I get with this type of problem is incorrect calculator entry. So again, please, please, please try this right now. Example B and C we will finish in class. So stay tuned for that. Thanks for listening and hope you have a great night.